So as you can see, the title here has changed slightly because as we were developing the content for this presentation, we realized what we were doing was characterizing DVL performance. So that's what we're really going to focus on at this time, but it has a lot to do with, involves calibration and verification. So there's a lot of overlap in these topics. So just to get started, I want to talk a little bit, get a little bit of a baseline so everybody's on the same page here. First of all, a DVL, if you're not familiar with what it is, it's a device that's used to measure speed relative to the bottom. And it's used in subsea navigation so that you have an Earth reference velocity. So what we typically do when we're using this is perform what's called dead reckoning navigation. And what we can consider here is first that there's a starting position, which you probably could get from a GNSS. And then you have the velocity, which will come from the DVL, a heading sensor, a time of travel, and an estimate and change of position. So what you do is you build up a trace of where you're going. So what I'm showing here is the star as a starting point, and then we have vectors composed of heading and velocity that allow us to see where we started and where we ended up to get ourselves a position. However, this is less than perfect, and if we were to look at the pure GNSS position, you'd have something that looks like this green line. That means that there is a cumulative error that builds up over time and distance. So this red line indicates that error. And what we are trying to do when we build navigation systems or we build DVLs is what we try to do is minimize this error by looking at all the sources of error and minimizing them. So now that I've said a little bit about error, what I want to do now is turn it over to my colleague, Audun, who is going to talk about error and look at this on the sensor level. So if you just give me a moment, I'll turn over control to Audun. You got it, Audun.
All right, thank you, Jostein. All right, so if we now, what we're asking here, of course, is how good is the DVL at measuring velocity? And whenever you ask the question, how good is some instrument at measuring whatever it's supposed to measure, what you're really asking is how accurate is it and how precise is it? And now that's in everyday ordinary language, accuracy, precision sounds like they mean about the same. So just to get everybody on the same page here, we'll define the statistical terms. So in statistics, accuracy deals with systematic errors. So for the DVL, that would mean errors that persist over time, whereas precision deals with random errors. And I guess everyone's probably seen these target analogies before. So if you look here on the left-hand side, we got someone, high precision shooter, not much spread here, but a obvious systematic errors well off, well off on this target here. So this is a low accuracy, high precision situation. Whereas on the right here, we got someone who's probably centered all right, but is all over the place. Shaky hand, maybe something contributing to a lot of random errors. So that's a high accuracy probably, but very low precision situation. So those are basically the definitions of accuracy and precision. And we might want to ask, what's going to cause problems here for a DVL? Now, if this is a shooting contest, it's not too obvious who would win out of these two. But for DVLs, we'll look at this again over time, because as Torsten was saying, we're not really interested in just the velocity typically from a DVL. We're typically interested in using this for navigation. So you're interested in position. So that's your velocity integrated over time. So if you have let's say a constant error velocity, that means that you will have a position error that grows linearly with time. So that's a pretty simple case there to analyze. Now, on the other hand, so this is the bias case. This is the where you have like 100% precision, right? No variations at all, but you have some accuracy problems. Now, in the other case where you have lots of random errors but no bias, we have to look at this statistically. So in this case, I've basically generated a lot of these potential navigation lines here. They all start out at 0, and then we get these random walks. So if I look at the distribution now, which I have to do at any one given time, it will still be centered at 0. So the expected error is kind of 0, but there will be a distribution that grows with time. And as that's represented, I guess, by these solid black curves here, which illustrate how one standard deviation of this positional distribution will grow with time, and that grows as the square root of time. So from that perspective, you can see that the constant bias, the accuracy issue here, is going to cause something that drifts linearly over time, whereas the standard deviation precision problem will cause something that increases with an error that grows with a square root of time.
I didn't get to ask a question here. When I look at the presentation of these plots, I see to the right with the ones that's showing the random errors. It seems like it's much more severe than what I see over at the constant bias. Am I misinterpreting this?
Right, yeah, if you look at the numbers, that's what it looks like. But then keep in mind that these are just some random numbers that I generated in MATLAB. And so in this situation, yeah, I would agree that and for this particular line, for instance, it looks like at this point in time, the random error here has grown faster than this constant bias. However, if we keep going for longer times, and this is why we refer to this as long-term accuracy. And if in particular, if you go to infinite time, of course, something that grows linearly with time will always outgrow what grows with the square root of time, right? No matter what the factors are in front. So again, we have to get back to what is the realistic time scale here. And for typical time scales of a DVL, doing navigation for line lengths of, let's say, a nautical mile, for instance, then we'll typically see that these biases, these constant or slowly varying biases, will dominate over these completely random errors. So we can look at trying to measure precision now first. Even though I've argued that this is the smaller contribution to the errors, typically we'd still like to look at a little bit how to measure them. Now, if I knew that my velocity was absolutely constant, let's say I was in a tow tank, and I knew that I was going at a constant velocity, I could just take the standard deviation straight off, right? Just measure a time series and take the standard deviation. However, if I'm doing this in a more realistic scenario out in a vehicle, that's actually not going to have an absolutely stable velocity. So I have to separate the true velocity variations from the noise variations. And to do that, we typically apply some spectral techniques. So if the motion is smooth enough, at least, that and that my sample rate is high enough that I can sample all the true motion and oversample a little bit maybe, then I can apply the spectrum. I'll find that the high end of the spectrum is completely dominated by the Doppler noise. So in this case here, I have my platform is actually a fairly large AUV that's very, very stable. So all the true motions of it is way down in the spectrum here, and the high end is dominated by the noise. So then I can just take this noise floor, and I basically just take the square root. This is the power spectral density. And take the square root, find, in this case, 1.1 centimeters per second. That's one standard deviation now of this time series. So if I keep doing this, I will find that this will be a function both of my speed over ground and the altitude above ground. So so this has to be done repeatedly if you want to truly characterize the DVL. Also, maybe if you don't want to do that, you can look at the figure of merit that the DVL itself reports. It does this for every ping, every beam. It reports an instantaneous measurement of the Doppler noise as one standard deviation of the noise. So now moving on maybe to the long-term accuracy. So how do we really define that now? So the long-term accuracy is then the accuracy of the DVL after we've taken all the necessary steps to remove all the manageable biases. And by that, I mean Static biases, so again, referring to that spectrum below, if I had something that was at 0 frequency, didn't change at all over time, that's really easy to manage because that's just a calibration, and those are gone. And at the high end of the spectrum, we've already argued that, well, those variations, if they happen at, over really very at high frequencies, then they're going to average out over the typical time frames that I'm interested in. So what's really our main focus here is the intermediate timescales, the slowly varying ones. Those are the ones that we try to minimize. Also, I should say that at the high end, now if you were interested in sort of the more high bandwidth, quicker motions, then DVL is good at. Then it's good to use the DVL with an INS, which has inertial sensors, which are really good at have very, very low noise, so they can measure variations on these short time scales, but they'll drift really quickly off. So the DVL is necessary to pull in this drift. So that's what the long-term accuracy is, really the bottom line for the navigation, also in an INS. So slowly varying biases. Let's try to see where they can come from. And we're going to be focusing on the effective beam angle. That's the one parameter now that's interesting. So let's have a look at this really simple figure first. So let's say that the DVL is over here, and what it does is it shoots off a acoustic pulse along this beam here and gets reflected from the seabed and then back up along the same beam. And what it measures, then what the DVL is able to measure, is the velocity projected onto this beam direction. So that's a Doppler velocity. That's what the instrument measures. Let's say now that I have a velocity component that I'm interested in along the x-axis. And for simplicity, we'll draw just a single component of velocity. Now in real life, of course, we have three dimensions in space, so we have 3 components that we need to measure. And we also have, well, 3 or 4 beams. Our DVLs typically have 4 beams, so we have enough to get all the components. But for a simple figure, let's stick with a 1 velocity component along the x-axis of our DVL, and this beam here. So now the single beam. Now, if I know the mounting angle of the transducer, I know which direction it's pointing relative to this x direction. I can easily find this, right? This is just simple trigonometry. I can just divide by the cosine of this angle. However, this angle may not be all that well known. Now, I drew this initially as kind of like a laser beam line here, but in reality, of course, it has a finite opening angle like this. So I'm shooting this over a spread of the bottom here, okay, kind of a large contribution from the seabed. Now, it's not too obvious here what the effective beam angle is anymore, right? Is it necessarily the center here? First of all, if I look at the edges of the beam here, okay, I can say that we can call this a whole bundle of these arrays here, right? And if I look at this one, it has to travel quite a bit further through the water column than this one does, right? So this one will be more attenuated than this one. So this one will contribute more, and that will increase the effective angle that I'm seeing. And the backscattering from the seabed will also have some dependency on the incidence angle here. And to make matters worse, that function also depends on the surface roughness of the seabed. So your bottom type there kind of dictates slightly also how this angle changes a little bit. So if I don't know exactly what this angle is, when I try to use my simple trigonometry to get back to this x component here, let's say I divide by the wrong cosine of the wrong angle, I'll get a scaling error. So that's one cause of biases, and this is one that we should focus the most on. And so yeah, it leads to a scaling error. So the error will be proportional to the actual velocity, but off by a factor.
So Audun, can I interrupt you and ask you, how does the whole calibration fit into this? When and where do you need to do it? What considerations need to be taken?
Well, right. So like I said, the surface conditions here on the bottom, like the roughness, is it sandy or is it silt? Is it rocky or is it muddy? That will come into account. So if I do a calibration on one type of bottom, and then I go, and let's say that I'm in a field and I want to do a large navigation job in this field, and that's a pretty homogeneous bottom type, then it's really ideal. Then if I could do the calibration first in situ, right, in this particular field, where I know that the bottom's not going to change that much. And also if I can do it at the actual altitude I'm going to operate, and with the same water parameters that I'm going to operate at, that's obviously going to give me the best result. Because if I take it somewhere else, my calibration is going to be slightly off at least.
Okay,
so yeah, so it depends. I mean, if you really want to get the absolute best out of it, you are best off by calibrating it where you're going to use it. But that's not always possible or practical.
Right.
So then we can look at, again, in practice, how to do this characterization and find the scale factor that we're interested in to characterize the DVL. So I've drawn here, again, some navigation lines. So here is my dead reckoning. This is my DVL in tandem with some heading sensor. And this has gotten me to this point. And at the same time, I'm also recording, since I'm doing this from a surface vessel now, I have GPS, so I have a good reference here. And I said that we should do long enough. I've said typically longer than a nautical mile. That's just a sort of rule of thumb. But that, again, refers to this long-term thing that we're talking about. Right, so now we're only really interested in where we ended up in these two navigation lines. So I'm going to just replace them with straight lines, and I'm going to look at the angle between them first. I'm going to call that the heading error. And that heading error, of course, will include any angular offset between my DVL and the heading sensor. So that's what you would normally remove in a calibration anyway. That you always have to do that. But when characterizing the DVL, we should also note that this angle here also includes any statistical error that the heading sensor makes. So whenever I keep doing this, for every line that I do, I should remove this error. If I'm only interested in characterizing the DVL, I should make sure that I remove the heading contribution from this navigation error. So if I now rotate it back so they're on top of each other, I can find that my dead reckoning with DVL error line here is a little bit longer than my GPS line. And the ratio of these two line lengths, that's the scaling error. And that resulted from my beam angle, my effective beam angle being slightly off. So
can I ask you what about the DVL's cross-track error? Won't that also affect this heading error?
Yes, in principle, but I'm going to argue that we can attribute virtually all of this angle here, all of this angle to the heading sensor itself. And the reason for that is that if I have, let's say that my X direction that I was talking about before is my direction of travel. So most of my velocity is being picked up along that X direction. Now, and my Y direction is now across the track, and that's going to be pretty small normally, okay? I may be drifting slightly, but normally that's a small velocity compared to my along the course. But both of them are going to be subject to biases, but both of those biases are going to come in the form of a scale factor, right? So if I have a very small cross-track velocity, and that's only off by, let's say, a 0.1% bias, then the contribution to that angle is going to be very, very small compared to the contribution from the heading sensor itself. So we're going to say that we're only going to look at the scaling error and say that that's the contribution from the DVL and the rest is from the heading sensor. An actual measurement of accuracy. So again, we want to go in a straight line that's long enough to achieve this convergence of the relative error. Now we're going to talk a little bit more about what that means. And the first thing to notice is that we really do need to have a good reference. Now the positional reference that I showed was with a GPS, and now it's not arbitrary what kind of GPS you use. If you just use a standard GPS with no corrections at all, I'd say the typical standard deviation in the position, it might be like 10 meters. So if you're looking at trying to verify that the DVL is better than, say, 0.1%, and let's say that if I was just to travel a 1,000-meter line, that would mean that the DVL would make an error of about 1 meter. And so if the GPS is contributing 10 meters, then that's going to totally dominate the error. So I want to make sure that the GPS contribution is way less than the DVL's contribution. So with an ordinary GPS, I might have to travel something like 100-kilometer lines, which is completely impractical. So a differential GPS where you can get the error down to maybe half a meter or a few tenths of centimeters would be good. That would leave you, then we would have to do straight lines for maybe a few kilometers. But an RTK is really good, because if you have an RTK system, the position error will be typically on the order of just a couple of 3 centimeters, maybe. So then that's really nothing to worry about anymore. And then we can look at the way that my relative error. Now, if I look at the position error relative to the distance traveled as a function of distance traveled, I should see that that should converge, because that's what I'm looking for, that long-term accuracy. So this convergence is critical. I should apply a sound velocity sensor to this, because the internal measurements of sound velocity are not accurate enough for this characterization. We'll get back to that a little bit later. I should also make sure, like I said before, to make sure to calibrate out any heading contributions to this. So this is only the scale factor. And I've also had to calibrate out the pitch, which is really easy on a surface vehicle, because I know that my elevation above sea level should stay the same. It should be 0 the whole way through. So that's the easy way to calibrate out the pitch.
Right. Can I ask, I have 2 questions I want to ask. First, when I look at this plot, can you sort of point out which part illustrates the precision error, and which part would be, or the random error that is, and which part is a long-term biases error?
Right. So what we said before was that at short times, we could see that the random errors might dominate. And that's really what we see here. I mean, at the very beginning, the relative error goes off the scale. All right. So, but it really quickly starts to converge, but still in this early area here, you see that the random errors are still dominating, but they should now subside here as 1 over the square root of time, or as the square root of distance traveled. And I should start converging towards my long-term accuracy. So at the very end of it here, where I've stopped, now I'm at about 0.06% maybe. So that's the bias, or the bias on this particular line. So when measuring long-term accuracy, that's the number I'm looking for. However, I would really, in order to characterize the DVL, I would really like to do this multiple times to get some statistics on it, because we know that the bias might vary with conditions.
Okay, so when you distill this down, you walk with the number you walk away with is a value of a bias for that particular line.
Exactly.
Okay, good.
Now we want to look at some of the other sources to navigation errors, just to put things into a little bit of perspective. So a heading offset now, for instance, just to get a sense of how important the heading sensor really is in navigation. So here is, if I just have, let's say that I have a mounting offset, then just for simplicity on the heading sensor. And we can look at how much of a percentage of position error will that contribute. So if I have like half a degree, if my heading sensor is off by half a degree, it'll result in something like 0.9% of distance travel error, which is well, it's not great. And also, I think 0.5 degrees is approximately as good as you're going to get with a magnetometer compass. I think that's like the best case. So if you have a DVL and you're using it along with a magnetometer-based system for hitting, you cannot really expect a navigation to get much better than 1%, say. So if you really want to get navigation down to the 0.1%, you're really looking at having your controlling your heading to better than just, I don't know, like a few hundredths of a degree down in this area here. Mm. Other main contributor, like we talked about, was the speed of sound. So again, if I plot speed of sound error in meters per second here, and looking at the percentage error here, now the speed of sound is in water, it's roughly 1,500 meters per second. So that means that in order to get to this 0.1% down here, I'm looking at being, that's equivalent to like 1.5 meter per second error. So my speed of sound sensor has to be, have errors less than a meter per second, well below a meter per second, I would say, in order not to dominate the errors. That should be done with an external sensor, and that can be either a direct measurement of sound velocity. You have those types of sensors, or you have sensors that of the CTD type that estimate from temperature, salinity, and pressure. Now, you can sort of do that with our DVL as well, except it doesn't measure salinity. It'll measure a temperature, which is good to about 0.1 degree, which will result in an error of about 0.5 meters per second. So that's, that hasn't blown the budget completely still. But the salinity, of course, is unknown. So you have to either guess it, or you can maybe use a CTD cast and then hope that it just stays constant through your operation. So let's say you do that, you're off by 2 ppts maybe, and you have this 0.1 degree error. That will result in a 0.25% scaling error, which is not terrible, but it's not exactly, well, it's not the highest level, and it's not good enough nearly if you wanted to characterize the DVL, because you should expect errors from the DVL to be like 10 times better than this. So you really do need to have an external speed of sound sensor. So those are some of those sources. Now, maybe Torstein, if you would like to
yeah, sure. So as you turn over control to me, I'm just going to say that now I'll speak a little bit about, pick up where Audun left off. So Audun gave us a good groundwork to show you what considerations that we have to take when we're trying to qualify our DVL. So we have to have good references, we have to give a good collection of sensors, and there's also a process involved when looking at the performance. So I'm going to give you a little bit of a picture of what we do here locally. So here's our testing grounds. They're in the inner Oslo Fjord. And one of the things that you see about this is that we have a variety of depths. So a common track that we take on the eastern side of the fjord here is that we can go from 10 meters in the silty bottom over here to muddy bottom at 20 meters, 60 meters, gets a little bit rocky, and then it's 100 meters and 150 meters, and then we wrap around and go back over the same track. So we get a great variety of depths for our sensors. And as I mentioned, the bottom is also complicated terrain. So you get many different types of slopes and many different types of bottom as well. So this will go back into what Audun was saying when he's saying it looks at the different way that the beam gets just mildly biased, which has consequences on our velocity estimates. So when we do this, when we're looking at the performance of our DVLs, what we do is we put it through the ringer to make sure that we look at everything in terms of bottom types and altitudes. And when we do this, we're also looking at both the detection rate and the accuracy of the DVL. A test setup. This is what we have currently. We have this vessel with a moon pool. And on the moon pool, you have a faired surface so that we do not create bubbles or noise around the DVL or its sensors. We have a sound velocity sensor here. that's pointing upwards, and then below that you can just see the crown, the bottom side of the crown to the DVL, and it's located up in towards the bow, so it's away from the motor, so away from noise sources. Then on the top of the cabin, we have a dual antenna GNSS. So we have an estimate of our heading comes from this. And for this, we also have an RTK correction. So that's what we use for a reference. And that gives us about centimeter accuracy. So that's what permits us to have relatively short lines that we can do because we have a very good reference. So how do we qualify the accuracy? So you know that this long-term accuracy is really the figure that manufacturers publish and end users are looking for when they're comparing and determining the performance characteristic. And what it means is if you remove all the static biases, this long-term accuracy is what remains. So this is what we're trying to characterize. But you can't simply do this by one calibration and one verification line. It's a statistical process, as we've alluded to. So one of the more common ways to do this is to look at what's called the circular error probability. And this is a way to figure out the maximum error for 50% of the targets. It's probably best if I just illustrate it here with a target, which we've used before. And what you can see here is if we shot 20 times and we picked out the 10 most accurate ones, 50% of the most accurate ones, what's the maximum error you can expect from this? And that's what this characterization is. It's a good reference to looking at the quality of any sort of targeting or positioning system. So let's look at an example of DVL 500, which we have tested not too long ago. And what you see here is a series of runs. We have 13 runs, I believe, here. And we did repeated ones, of course, to address the statistical variability. And that's exactly what you see here. We have one line that is used for the calibration of the system. When I say the calibration, it's the calibration of the scaling factor. And all these other estimates are variations of that. And you can see also that what we're doing is presenting it as a function of altitude. Now, it's probably interesting at this point to point out that if we just went out and did a simple calibration, and then we had one verification run, the next one in line would have been this one just nearby 20 meters. And that would be extremely accurate system. And the point here is that you have to be careful and as end users be a little bit skeptical when you see presentations of data that show you this one run and this one verification and look how wonderful it can be. I think the question to ask is, instead of seeing cherry-picked data, to look at a body of work. And picking out just one very good run it's common for all of us to do, and I've probably been guilty as much as anybody about doing this because you tend to remember really the good runs, but when you start logging a lot of data, you see what the real performance is like. Nonetheless, I should point out on this particular DVL, on this particular day, if we look at the CEP 50 in this green block here, you see that it's around 0.02%. So of course, we're very pleased with that.
Yeah, that's a good result, Doshin. And also, as you pointed out, there's no real trend with altitude here. So now that we've done such a great job of removing all that bias, why is the spec still at, what is it, 0.1% still?
Yeah.
Just 5 times better. When are we going to reduce the spec?
Well, this is indeed a new firmware, so we're not going to do a knee-jerk reaction and just say, yes, this is the new spec. I think what we want to do is build up, as I said, a body of work. It's pretty good to get some statistical sense of what's going on here with this data that we have, but I think we need a little bit more time. And I think, we've always been a little bit conservative about giving what we give out for specifications of our instruments. But I'd say that, this really does look promising the ways that we're addressing altitude and the corrections that we're able to make now. So, but yeah, you know, I think we can expect to see the specification come down. So we're optimistic about that.
Okay.
So summary. So developing a dependable number for the long-term accuracy is a statistical process. It requires a collection of trials and an attention to what you're doing in the error sources. The completeness of the process involves a range of altitude and bottom types, and it really shouldn't be done over the same piece of bottom. I mean, a lot of system tests that you've seen out there, they'll go back and forth over the same piece of bottom. That doesn't really provide a statistical variation of the process. It's interesting to note that this process, which we do for qualifying our DVLs, is also very similar to what's done to apply to a navigation system and in evaluating a navigation system. So you have to consider that it's only good as the reference that you're using, and the error of the navigation system is the sum of its parts.